Hello math friends, welcome back. This is AP Calculus section 3.5 day 3 notes. Today we're going to continue talking about the chain rule and we're just going to dive right into our example 1. It says if f is the function whose graph is shown, let h of x be the composition f of x and let g of x be the composition f of x squared. Use the graph of f to estimate the value of each derivative. So for letter A, they want us to find h prime of 2. All right, so how are we going to do this? Well, let's begin with what h of x was given as. H of x is given to be the composition f of x. So if we want to find h prime of 2, then we first need to find an expression for the derivative of h. So h prime of x would be equal to, now we know we're going to have to use chain rule because we have a composition, and chain rule says we differentiate the outer function at the inner. So that would be f prime of x times, and then the derivative of the inner, which would be f prime of x. And now if I want to know h prime of 2, I just need to plug 2's in everywhere that x appears in my expression for h prime of 2. All right, well now it's time to use the graph because I need to know what is f of 2 and I need to know what is f prime of 2. Well, f of 2 is just going to be the value of the function, the value of the function when x is 2. So when x is 2, the value of my function is 1. So this becomes f prime of 1 times f prime of 2. So now I need to figure out, well, what is f prime of 1 and what is f prime of 2? Keep in mind, f prime of 1, that is going to be the slope of f of x at x equals 1. And f prime of 2 is going to be the slope at x equals 2. So first, let's look at x equals 1. X equals 1 is right there. And so when I look at the slope of my graph right there, kind of looks like it's about down 1, right 2. So that would be a slope of -1/2. And when I look at x equals 2, the slope right here looks like it's about down 1, right 1. So that would be a slope of -1. So h prime of 2 is going to be equal to the value that I get when I multiply -1/2 times -1. So h prime of 2 is equal to 1/2. All right, let's take a look at letter B. Letter B asks us to find g prime of 2. So again, let's begin with the given function for g. G of x is equal to f of x squared. And so if I were going to find the derivative of g, which would be g prime of x, I will be using chain rule. The derivative of this would be f prime of x squared, the derivative of the outer at the inner, times the derivative of the inner. Well, the derivative of x squared is 2x. And now if I want g prime of 2, again, I will be inserting 2 for x in all locations where x appears. So now when I simplify this, g prime of 2 is going to be equal to f prime of 4 times 4. So again, f prime of 4, this is going to be the slope from my graph at x equals 4. So when I find x equals 4, it's right here, and I look at the slope, looks to me like I'm going up 2, right 1. So this would be a slope of 2. times that 4, so I get g prime of 2 is equal to 8. In the second example, we are not given a graph. Instead, we are given a table of information. And it says, if g of x is equal to f of x, use the table to estimate the graph of g prime of 1. Well, first of all, let's start with what g of x is equal to. G of x is equal to f of x, which is a composition. So we know g prime of x is going to be equal to f prime of x times the derivative of f of x, which is f prime of x. So if we want g prime of 1, we have to put a 1 in for x. All right, and I can figure out f of 1. That's going to be a value from my table, right? When x is 1, right here, f of 1 is 2. So then this becomes f prime of 2.0 times f prime of 1 is my g prime of 1. But now again, remember, primes, derivatives, are slopes. So now this this right here is going to be the slope at x equals 2, and this right here is going to be the slope at x equals 1. But this time we do not have a graph to look at. All we have is a table of values. So the best thing that we can do if we're trying to figure out our slopes is we can use ordered pairs, and we can find two slopes that would be close approximations, and we can average them together. So let's start with f prime of 2.0. Okay, if I want to find that, I'm actually going to find two different slopes. So here is x is 2, right, 2.0. So I am going to find the slope between these 2 points, and I am going to find the slope between these 2 points, and then I'm going to average them together. And that's going to be a pretty decent guess based on the information that we have for the slope at 2. So my first calculation will be 4.4 minus 3.1 over 2.5 minus 2, which is going to give me a slope of 2.6. And then my second calculation will be 3.1 minus 2.4 divided by 2.0 minus 1.5, which gives me a slope of 1.4. And then if I want to average those two together, I'm going to take 2.6 plus 1.4 and divide by 2, and I'm going to get an average slope of 2. So right here, 2 is the value that I'm going to use for f prime of 2. Now I need to do the same thing for f prime of 1. So f prime of 1.0, I need to choose some ordered pairs. Here's my 1.0 right here. So I am going to use these 2 points to find my first slope. I'll do it right now. 2.4 minus 2.0 divided by 1.5 minus 1.0. You do the math and you get a slope of 0.8. And then my second 2 points that I'm going to use are going to be when x is 0.5 and when x is 1. So 2.0 minus 1.8 divided by 1.0 minus 0.5. And that gives me a slope value of 0.4. And so then if I want to find the average of these two, hopefully you can do this in your head, but I'm just taking 0.8 plus 0.4, which would be 0.12. I'm dividing by 2, which gives me 0.6. So right here, this value is going to be 0.6. So finally, if I want to find my g prime of 1, 2 times 0.6 gives me a value of 1.2. My final example in this set of notes doesn't really have any calculations. It just deals more with understanding the relationships between position, velocity, and acceleration, and the fact that acceleration is actually a composition function. So let's talk about that for a second. Acceleration is the derivative of the derivative of position. So it is a composition. And just in case you're not seeing that right away, let's write this out. If we say S is our position function, then we know that V, our velocity, is going to be the derivative of our position. And we know that acceleration is going to be the derivative of our velocity, which is going to be equal to the derivative of our position. So now you can kind of see how acceleration would be considered to be a composition. So this example says a particle moves along a straight line with a displacement s of t, there's our position function, a velocity v of t, there's our velocity, and an acceleration a of t. Show that a of t is equal to v of t times dv ds. Explain the difference between the meanings of the derivatives dv dt and dv ds. Well, first of all, let's do that. dv dt would be equal to the derivative of velocity with respect to time. So derivative of v with respect to t. And dv ds is going to be equal to the derivative of velocity with respect to position. So with respect to s, which is our distance traveled. So if we think about, if we start with the fact that, and again, I'm going to just kind of rewrite this, our position, that's our s of t function. And our velocity, that's our v of t function, which velocity, remember, is the derivative of position with respect to time. So that's going to be equal to ds dt. And then our acceleration, this is the one they want us to show here, which we call a of t, is equal to the derivative of velocity with respect to time. But we know that that's actually a composition, that's actually equal to the derivative of velocity with respect to position. That's the derivative of the outer at the inner, times the derivative of position with respect to time. Okay, so let's label these. This is the derivative of the outer at the inner. And this is the derivative of the inner. Okay. Which ultimately is equal to the derivative of velocity with respect to position times our v of t. Because remember, v of t is actually derivative of position with respect to time. That's what velocity is. So we just showed what they asked us to show, that a of t is equal to v of t times dv ds. Derivative of velocity with respect to position.